This NASA's Psyche mission is an electric journey to a metal world. And I wanted to give acknowledgement to our principal investigator, Linda Elkins-Tanton at Arizona State University. She's, again, as I've mentioned, she's our principal investigator for this mission, and it's a discovery class mission, fairly large, relatively speaking, compared to some of the other missions that we have. I am the Psyche program executive at this point, and I'm the Science Mission Director of Planetary Science Division at NASA headquarters. So first off, I wanted to say that, you know, this is obviously me giving the talk, Lindy being the PI, but there are a lot of people, and you see little snippets of about 100 people here. That's not all that we have running this project. This project is many hundreds of people, and everybody is an important part of the team. I don't know if you can see my cursor when it moves around. Can you see it?
Yep.
So the person that I'm circling right here is Lindy. She's the principal investigator from Arizona State University. And this is Henry Stone. He's the project manager at California Institute of Technology's Jet Propulsion Laboratory in Pasadena, California. And this person here is Carl Adams, and he was the previous program executive, and he retired about 4 months ago, and I've taken over for him. So I'm still a relative new person on the project, but I did want to give acknowledgement to those couple of people, and of course everybody else, that if I named them all, we'd be done with the presentation. So first off, what is Psyche? And I mentioned that it was a journey to a metal world. This is the largest known metal asteroid in our solar system, about 200 kilometers across. Figure that's on the order, if you just use a three foot per yard or 3 foot per meter, that's on the order of 600 feet in diameter. We expect it to be 30 to 60% metal by volume, which is a rarity. And what we're trying to prove here with this mission, with this science mission, is Psyche the exposed core of a disrupted planet formation? So was there a planet that was being formed and something happened to it? Say it was struck by another asteroid or struck by a large comet. We have a science payload on here with 3 main types of instruments. One is a multispectral imager or camera. One is a magnetometer that will be used to see if this asteroid has a magnetic field. The other one is a gamma ray neutron spectrometer that will be used to help us determine what the materials are that make up this asteroid. And this is also, we have a technology demonstration on here that's being done in conjunction with the Space Technology Mission Directorate at NASA headquarters. It's going to be our first use of Hall thrusters beyond lunar orbit, and I'll tell you a little bit more about those as we go through the presentation. So where is Psyche? You know, I've mentioned that it's an asteroid. It's actually designated as asteroid 16 Psyche. That's its real designation. It was discovered back in 1852 by a guy whose name I can't even pronounce, but it was just seen as a tiny little dot of light in the sky at that point in time. But where is it, basically? Well, here's its orbit within the asteroid belt. So you can see it's definitely outside of the orbit of Mars and inside the orbit of Jupiter. It's not near Earth, so it's not at this time an asteroid that would pose a threat to us in particular. This is a picture that was actually taken from a fairly good telescope that was put in the backyard of Lindy Elkins-Tanton, you know, our principal investigator. So that area that is circled there, that little tiny faint dot that you see there, is actually the asteroid Psyche, which she was pretty happy to be able to actually see it from her own backyard in Arizona. So to give you an idea of how big it is, and don't get nervous, this is not where the asteroid is going to hit the planet or anything like that. This is just to show you, with respect to Arizona, you can see how big this thing is. And we've put Massachusetts in there as well to show the difference in size between Arizona and Massachusetts and the asteroid. So it's fairly big. If this was a planetesimal, if this was something that was already out there, and the expectation is that this thing was probably hit by something else, a large meteor, another asteroid, a comet perhaps, what would have happened to it? Well, it would probably have broken up into pieces, but the gravity would kind of try to pull it back together. And as it was coming back together, if it had any molten components of its core, as opposed to being solid, you would see these things erupting on the surface of this broken up piece. You would, because of these components of fluid that are moving, you would see a magnetic field forming, and that's what we would end up with. This is imaging that has been done by a facility called SPHERE, okay, which stands for the Spectropolarimetric High Contrast Exoplanet Research Instrument, as part of the European Southern Observatory. And what they did here is they took various images of the asteroid as the asteroid was rotating to try to get a general idea of what its shape looked like. It's useful for us to have that if we're going to try to go to this asteroid, which is what we're going to do. We're actually going to go to it, and we're actually going to orbit it with the Psyche spacecraft. So knowing what its general shape is like gives us some information that we need to be able to feed back into our guidance, navigation, and control team who are out at JPL to figure out how to put this into the proper orbit around the asteroid. So this was a mission that was selected. What NASA tends to do is they'll put out AOs. AOs stand for Announcements of Opportunity. They released this announcement of opportunity in late calendar year 2014 after having, and the Psyche team were a number of scientists who had been discussing that this would be a good thing to go to. We wonder if when Discovery has its next AO released, if we should submit for it. So they submitted it as a step 1 proposal. It won. They submitted their step 2 proposal, and then they were selected at the beginning of 2017. So at that point, we went into what we call phase B, which is formulation, where they come up with a better design for what things should be looking like. We go through something called a preliminary design review, a PDR. The PDR is where we at NASA decide whether or not we're going to continue to go forward with the mission. Up until this point, it's pretty much vaporware, right? So at this point in time, we look at the design very carefully. We have a number of experts that look at the design on review panels. They make a recommendation to our associate administrator for the Science Mission Directorate, and he decides whether or not we, and that's Dr. Thomas Zerbuchen, he decides whether or not we select the proposal and confirm it for going forward into phase C. So we had the PDR in the beginning of 2019. The mission was confirmed for implementation, and they went into a critical design review in 2020. So during this time, this is where we're actually going to build the spacecraft. And building spacecraft means building what we call the spacecraft bus, which is what carries the propulsion system, what carries any things that we need for the propulsion system or for communication, like the solar arrays, because we actually are running off of electricity for the most part. And this is interesting because we're going to be roughly 3 AUs out from Earth. So that's 3 times the distance from Earth to the sun. A long distance to be running on solar panels. And our goal was then to launch by early fall of 2022. And in fact, our plan was to launch in August of 2022, which is why we have a "We Are Here" line here, but you'll see I have a giant X through that, and I'll explain why. We got into an issue with the guidance, navigation, and control flight software. And this software is very important on the spacecraft. We have made spacecraft so smart that they are able to fly quite a bit autonomously. they make decisions on their own as to how they have to fly, where they have to fly. We program enough of the information into them, but then they go and they do this themselves for a large part. For Psyche, that's important because for a good portion of the time that it's flying, the antenna is not pointed back towards Earth for us to be in communication with it. So we actually have to turn the spacecraft around when we want to talk to it. If this guidance and navigation and control software is not rock solid, we don't have a mission. And so what happened here is, primarily because of impacts that we've had from COVID over the past couple of years, which restricted people actually being able to be on site at the Jet Propulsion Laboratory and at Maxar, the company that built the propulsion system for us and the propulsion system bus, that slowed us down drastically. But of course, what doesn't slow down is the planetary geometry of where Psyche is, where Earth is, where the sun is, and where any other planetary bodies are that we may need along the way. And what we may need is important here. When you think about it, this is a mission, and you'll see a little bit later on, this is a mission where we get what are called gravity assists by flying by other objects. And in fact, this mission was designed to fly past Mars and do a kind of a slingshot trajectory past Mars to put it on course to get to Psyche. Mars is tricky because we can only launch things that are headed towards Mars every 18 months. And again, that's just because of the geometry of where Mars is with respect to the Earth. So JPL and the Psyche project realized just several weeks ago, in fact, that they could not reliably get all the testing done in time to make this 2022 launch window. And so they requested a delay. We're looking at the delay right now, and they are trying to determine what other launch opportunities, if any, are viable for us. So far, they're thinking that there may be opportunities in the 2023 and 2024 timeframe, and NASA is going to entertain those with a whole host of other options for the mission. And so we're looking at that. We're about to start looking at that extremely carefully next week, in fact, with a bunch of meetings that are going to be held at JPL. So just as an idea to give you the size, relative size of the spacecraft, and I did not draw this, although I don't know if I could have drawn the little human being to look any better than what it looks like there. This is kind of relative size of the spacecraft. So you see it's larger than a person, an average adult. You'll see the main instruments called out here. The imager is over on that side. You can see it roughly in this area here. Magnetometers are these tiny little nubs that are sitting at the top of this boom. The gamma ray spectrometer is up here, and the neutron spectrometer here. And then this is DSOC. This is a deep space optical communications technical demonstration. What this allows us to do, and we want to prove this, is instead of communicating with standard RF radio waves, basically, we're going to go into the optical frequency realm and do our communications back to send command and telemetry, commands to the spacecraft and telemetry back from the spacecraft, basically on laser light. And trying to do that has its own challenges. Pointing has to be much more exact than it has with standard RF. And you have to deal more with cloudy days than you have with other things because the light doesn't do as well when it hits cloud cover. But that's part of this demonstration. So that's riding along on Psyche. There's also something that I don't mention as part of this presentation, but Psyche has kind of a hitchhiker going along with it, a mission called Janus, which is a much smaller mission. It's two small spacecraft. They're called smallsats, roughly weighing about 100 kilograms apiece. And each one of these spacecraft are going to fly to two different binary asteroid systems. One system is a very well-behaved system. So you have one larger asteroid with another smaller one, basically a moon, circling around it. The other system is very chaotic. So it's an asteroid with a moon that's circling it, but this moon is very chaotic in behavior, that it's not a stable orbit. It goes in, goes out. So that mission is what's called a ride share, and that's riding along with the launch vehicle, because we have a large enough launch vehicle that we can carry more of a payload. We can literally carry more mass along with us. And so Janus is a ride share. So it right now is also ready to go, but it can't go right now because we have to wait until we have a new launch opportunity. When you see the spacecraft with the solar arrays unfolded, you'll get a better picture. The center of this is, again, the spacecraft, and you're looking, at this point, you're looking down onto the communication antenna that normally will be pointed back towards Earth when we have to be in communication. Here's the human size over here. You'll see this is 24.7 meters across, and these are the two solar arrays, kind of cross-shaped solar arrays, and 7.3 meters across here. So figure multiply by 3, 70-some feet across. So it's a fairly large object that's going to be out there flying. Of course, it's in zero gravity, so it shouldn't have any major issues flying. So how do we launch? Well, we're going to launch with SpaceX. NASA works very closely with SpaceX. SpaceX has been an excellent partner for us. We're going to launch, and we were scheduled to launch, and we actually have the launch vehicle at Cape Canaveral, Florida at this point in its various pieces. We didn't stack it up on the launch pad yet, and we won't for now because we're not going to launch now. But if we were to have launched in the August to September timeframe, we were going to launch on, this is called a Falcon Heavy. A normal Falcon is this part up here, which is the payload fairing. This is where our spacecrafts sit inside here. This is the main booster. If this was a simple Falcon, it would just be this single stack. Falcon Heavy has these two side boosters on the side, and this is currently the most powerful rocket on the planet that we have. Now, NASA is developing its own Space Launch System, SLS. First launch of that is Artemis 1, which will be coming up within the next month or so. And that will be ultimately be the largest launch vehicle we have. That's going to be the launch vehicle that we use to send humans back to the moon and to send humans to Mars. We could probably send humans to the moon on a Falcon Heavy as well. And they've been getting, as you've heard, flight qualified with humans because SpaceX has been launching humans to the space station. So we're going to have multiple ways of getting there at this point. So this trajectory here, I had mentioned before the Mars Gravity Assist to you. And this was designed for an August launch opportunity, right? Concept being that we launch here from Earth, from Kennedy Space Center in Cape Canaveral, Florida, and our launch date was originally August 1st, 2022, so it would have just been a few weeks from now. We launch, and then by May of 2023, we would have gotten to Mars. Mars would give us a gravity assist and throw us out here onto this trajectory to get us to Psyche itself by January of 2026. And remember, I said it was about 3 AUs away. At this point, it'll be 2.7 AUs away. Following through the orbit, it will make its way to being about 3.3 AUs by the end of when we're doing operations. And we have 4 phases of operations here. Phase A, Phase B, Phase C, and Phase D, which we'll explain a little bit later. And then DSOC prime mission operations that are being planned or are supposed to be planned in this time frame here. So the initial checkout would have been about 70 days. The first cruise phase would be Earth to Mars. We get the Mars gravity assist. The second cruise phase would then be Mars, giving us a slingshot trajectory to get to Psyche. DSOC operations for the optical comm demonstration would be from launch until about 1 year. But recall, we would get to Psyche in 2026, and we would continue through October of 2027. So almost 2 years of operations at the asteroid itself. And this here shows it slightly differently, where you can see more detail on what these orbits are. The first orbit in what we call this period here, operations orbit A, would be at about a 700-kilometer altitude above the asteroid. It would be for 56 days, and the prime portion of this part of the science mission would be to measure the magnetic field, do some imaging and mapping of the surface. Once we would get into orbit B phase here, we would have lowered our altitude to about 290 kilometers. We'd stay there for 80 days, do about 169 orbits at that lower altitude, and we would get the topography and geologic mapping while continuing our magnetic measurements. So now we would have the topography, we would have it in multi-dimensions. Orbit C, coming down even closer, 170 kilometers for about 100 days, which would be 362 orbits. Each orbit is only 6.7 hours in duration. This would be to measure the gravity field at the moon. And I said the moon. See, that was a slip of the tongue because I previously worked on a mission called GRAIL, which was a lunar mission, and GRAIL stood for Gravity Recovery and Interior Laboratory, GRAIL. And that mission was 2 spacecraft that went to the moon. And by the 2 spacecraft being in very precise orbits and communicating data back and forth to each other, they were able to map the gravity field of the moon and map what the moon's structure looked like from its crust all the way down to the core. The person who was the principal investigator on that was Maria Zuber. I worked with her quite a bit. She's in charge of geosciences at Massachusetts Institute of Technology, MIT. Excellent scientist. And she's one of the co-investigators on this mission as well. So she would be doing this gravity portion of the mission. And then when we would go into orbit D, we would drop down, we would cut this in half. We would go to 85 kilometers, either for about 100 days, and we would be measuring the composition. So the composition will tell us what type of metal is this made of, what are we doing at this point in time. So you see 4 different types of science orbits over a 20-month period, getting to this minimum altitude of 85 kilometers. We say all electric operation and using over 1,000 kilograms of xenon. So I'm saying electric and I'm saying xenon. Xenon is a gas, so how does that equate to electric? So let me real quick show you again what these payloads look like. These are the actual instruments. So this is what the magnetometer looks like. It's built by the Danish Technical Institute, DTU. The multispectral imager, or the MSI as we call it, which is used for imaging, topography, and composition, built by Arizona State. Gamma ray and neutron spectrometers, built by the Johns Hopkins Applied Physics Lab, where I worked for about 20 years earlier in my career. And these are those 2 components. This is the deep space optical communication for high-speed laser comm from Earth vicinity, hoping to go to Mars and beyond. And the reason we're doing this is that when we know we send humans to Mars, we don't want to have a slow rate of data return coming back. We want to be capable of doing high rate data and high quantities of data. And to be able to do that, you need a very, very fast link with a lot of bandwidth. We want to be able to do basically high definition video from Mars. And it takes a long time to get a signal back from Mars. So this is a very important technical demonstration that we're going to do. Here is the spacecraft very early on in the clean room where it's being built. This is called the high bay clean room area. You'll see people walking around in here. This is kind of a fisheye lens, so everything looks a little bit curved here, but you'll see people walking around in clean room garb, which kind of gets cleaner over time, right? The idea is we want to make sure the spacecraft doesn't have any contamination on it. For a variety of reasons, we don't want to have instruments get contaminated. If some contamination comes off of one part of the spacecraft and migrates to another. We've seen this happen on missions before where there could be some particulate matter that comes off of the main spacecraft structure and winds up on the lens of a camera. So the camera no longer has a clean image anymore. We don't want that to happen. We also don't want to, if we go someplace, and we actually end up landing someplace. Not that we've planned to do that here with Psyche, but we did plan to do that with a much earlier mission called Near Earth Asteroid Rendezvous, which went to an asteroid called Eros, named after the goddess of love. We actually managed to launch that out of, that was a mission done at APL in conjunction with JPL, who did all of the navigation for us. Not only did we get to that asteroid successfully, but instead of disposing of the spacecraft by firing the main engine and sending it off into deep space, we decided to land on the asteroid. So we were the first spacecraft to actually land on an asteroid. We didn't have any landing gear or anything, but we found a way to land it down so it just kind of sat on its solar panels and sent us some images back until its battery died. So that was great. Here you'll see, as you'll notice, that the spacecraft has kind of beefed up a little bit over time. You'll start to see these reddish structures that are showing up here on the spacecraft. These are actually our thrusters. So this is what's providing the thrust to keep the mission moving. And these are what are called Hall thrusters, or Hall effect thrusters. They were installed back in August of 2021. And so what do these have to do with anything? Well, these tanks up here contain xenon gas. And the xenon gas is the fuel for these thrusters. The gas is not under pressure such that we're releasing the gas and the pressure in the tank is thrusting the spacecraft. What happens is we open the valve for the xenon gas and allow the gas to be pulled out by an electric field that is set up around the gas. And this electric field it ionizes the xenon and causes the xenon to accelerate out from the thruster. The bright blue that you see here that's coming off, and you can actually see the trail of it coming off here, is the xenon gas being expelled out the back of the thruster. And that is what provides the propulsive effect for the spacecraft and allows it to move. And so, as I said in a much earlier slide, these Hall thrusters will be the first ones to be used beyond the lunar orbit. So it's, again, these in and of themselves are not going to be a tech demo, but it's going to be the first time that we use it, thinking that it will probably do a pretty good job of propelling us and getting us there. Thruster design like this is very important because when you start to put things like hydrazine fuel and oxygen, large tanks of fuel on board a spacecraft, it becomes very heavy. The heavier the spacecraft, the bigger the launch vehicle you need. And we do max out. We can only launch so much with any of the spacecraft, with any of the launch vehicles that we have on this planet right now. You have to be within the mass limitations to be able to actually carry science instruments that can actually do the detection that you need when you get to whatever target you're going to. That's very, very important. So thrusters like these are relatively small. And because they're relatively small, it makes for a system that is relatively lightweight and allows for more mass to go into the science instruments and the other part of the spacecraft that are needed just to communicate with the ground. We have to have a command system that reads the commands that are sent up from our deep space network so that the spacecraft knows what to do. It has to store data on board the spacecraft. The spacecraft then, when we're ready to get that data back down, it plays back that data for us, and it's done over one of the Deep Space Network main facilities. There's 3 main facilities on the planet that do this. One is in Goldstone, California. One is in Madrid, Spain. The other one is in Canberra, Australia. So these are all roughly 120 degrees of longitude apart. It allows us to have nearly continuous coverage as the Earth rotates to communicate between one station or another, and we do handovers between stations if we need continuous coverage. So this is a very fascinating technology, and it's one that's we're hoping is going to be used more and more over time. So now, what else do we have to do to prepare to launch one of these things? So again, we're back at JPL. We're showing the spacecraft is getting ready to go into environmental testing. What is that? So space is a harsh environment. You've heard that said before. It's a vacuum. It's cold. Depending on where we're going, the spacecraft could be in a very hot environment, right? If a spacecraft goes and is slingshotted around the sun, it gets a lot warmer. We had to do things like that with a couple of missions that have had to have, like the Parker Solar Probe, had to have a special type of insulation put on so that the entire spacecraft didn't melt because it got so close to the sun, and it's working phenomenally well. But we have to make sure that we have a spacecraft that can handle the changes in environment, make sure that the instruments and all the various subsystems on board can handle these changes in temperature. So that's part of the environmental testing. It's temperature. It's also dealing with being in a vacuum as opposed to being within Earth's gravity. There's no real gravity in space that's tugging at the spacecraft. So how do the components work in close to a vacuum? So we go into the chamber, and you'll notice that the chamber that they have at JPL can handle a spacecraft a lot larger than Psyche. So even though Psyche seems like a large spacecraft, they can handle a lot more than that at JPL. We also go and do vibration and shock testing, because when we launch, these poor spacecraft get quite a ride. The launch vehicles shake the spacecraft quite a bit. And so this is a giant vibration table that you'll see it sitting on here. That table will shake the spacecraft quite a bit. We want to make sure that pieces don't fall off, obviously. We want to make sure everything that's bolted down stays bolted down, and make sure that everything continues to work after it's been vibrated, simulating the launch environment. So here's the spacecraft with the solar arrays off. They're getting ready to put the solar arrays on to do some more testing. This was just back in February of this year. And I'm showing this picture again so you get an idea of what the solar arrays look like with regards to human size and the rest of the spacecraft. Notice the 3 sections here on each side. Those 3 sections are what you see here. This is one wing going this way horizontally with 3 sections in it. The first section up to this gold stripe. The gold stripe is the hinge. The second section up to the gold stripe is a hinge, and then the third section. This is partially deployed because in space, what will happen is there are 2 hinges here and here that will deploy the other pieces up and down to form that cross that you're seeing on each side. So that gives you an idea of how big this thing really is when it's going to be out in space. So there we have people looking, making sure that the xenon tanks and everything are in and everything is sealed up nicely. It's just about ready to go. So we're getting ready to ship the spacecraft. Oh, and this is me to prove that I actually work on Psyche. We were pretty much sealed up here. You'll see a lot of the insulating material had been wrapped around the spacecraft at this time, so you can't see much on the inside. I had to wear a mask. This wasn't because of COVID. It was because of contamination of the spacecraft. And the only reason I had to wear this mask was that when I'm facing the spacecraft, I had to have a mask on, because if I breathed air onto the spacecraft, it could contaminate it. So when I stepped a little further away, they let me take the mask off as long as I didn't turn around and look back at the spacecraft. So then we have to get the spacecraft to the Cape. And of course, this is something that's built out in Pasadena, California. We have this giant shipping container that the spacecraft was kind of folded up and put into to send it there. And it's big, so it doesn't just fit on any particular airplane. So what plane were we going to use for this? Well, we're actually going to use the Antonov 225 Miria, or dream. This is the world's heaviest and largest aircraft. This is a picture of it in Donetsk, Ukraine on July 26th of 2011. This was the aircraft that we had scheduled to use. We had reserved it, scheduled to use it. It was going to get us there with no problem whatsoever. And then we had the Russians invade Ukraine, and here's the aircraft today. So it was destroyed by the Russian attack. Adding to the tragedy of the humanity lost within the Ukraine from this attack, we no longer had a ride to get to Cape Canaveral. So we had to scramble, and it's not always easy to get an airplane that can fit something like this. We did ultimately get a Boeing C-17 cargo plane, and you can see in the very back here that is the rest of the shipping container that is going to come out of this cargo hold as they take the spacecraft down to the Cape. So here again, this is a more recent picture after the spacecraft got to the Cape. It got to the Cape at the very end of April or beginning of May, so it's only been there a couple of months at this point. You can't really see what they look like here because they're all kind of buttoned up in what we call the bunny suits. They have to go through a lot of scrubbing before they're allowed to go in with the spacecraft at this point. No exposed hair other than eyebrows. They have these little booties on, these suits, these gloves. You'll see Lindy here has these gloves on, and then this is Henry Stone, the project manager, and Lindley in the clean room high bay shortly after delivery. We're still down there right now. We're still in a high bay facility that Kennedy Space Center has for us. We've asked them to look into options of where we can be stored, because we can't stay in this high bay because there are other spacecraft that are coming through and being processed through. If all had gone as planned, we were going to be launching off of pad 39A, which was the historic launch pad that launched Apollo 11. And SpaceX has use of that pad now. And this was going to be a spectacular summer launch for us. It's not going to be this summer. We have our fingers crossed, hoping that technically it works out, that we're able to work out the technical aspects and the financial aspects of this, because when anything happens with a large spacecraft like this to delay it, there are costs to it that are money costs, and so we have to see if we can actually afford to launch this. So please stay tuned for developments. There's always going to be posts about Psyche out there on the Psyche blog.